All right, subscribers, welcome back to another episode of Science with Surbeck. Today, what we're going to be talking about is section 3.2, which deals with changes in matter. Now, before we get into the details of notes, there are a few objectives that you should be able to meet by the end of this video. Objective number 1, define physical change and list several common physical changes. Objective number 2, define chemical change and list several indications that a chemical change has taken place. And objective number 3, apply the law of conservation of mass to chemical reactions. So we start out here with physical change. And physical change is defined as a change that alters a substance without changing its composition. Now, a good example of a physical change would be crumpling up a sheet of aluminum foil. Now, before crumpling up that sheet of aluminum foil, it is a smooth, flat, mirror-like sheet. And after that sheet of aluminum foil is crumpled, it becomes a round, compact ball. Now, it's also important here to identify some other examples of physical change. One simple, easy example is cutting a sheet of paper. Another example would be breaking a crystal. Now, it's important that we identify some of the terms that are associated with the physical changes. 1 is bend, 2 is grind, 3 is crumple, 4 is split, and we also have crush. Now, again, these are only a few examples of the terms. Just keep in mind that physical change, it's going to alter the appearance, but it's not going to change the composition, which really means for us, if you want to think about this, we have no chemical reaction taking place with a physical change. Now, one specific type of physical change that we can talk about, and we've talked about it up to this point in this chapter, is that of a phase change. So let's remember that a phase change is defined as a transition of matter from one state to another. And with phase change, in section 1, we had that triangle chart that showed each of the states of matter, solid, gas, and liquid. And then it described each of those phase changes associated with that particular diagram or chart. Now, what we have to keep in mind with phase change is that the temperature and pressure changes will change the state of matter. And so, again, another great example of this is water, H2O. So the first thing here is that if we are at or below 0 degrees Celsius and under atmospheric pressure, which is 1 atmosphere, the water is going to be in the solid state. Now, this solid state of water is known commonly as ice. Now, if we add heat to this ice, it will eventually melt to become liquid water. Now, as you add more and more heat to that liquid water, eventually you get to this point at 100 degrees Celsius or above under that standard atmospheric pressure, which is 1 atmosphere. The water begins to boil and liquid is converted into steam or water vapor. Now, just as a reminder for this process, I didn't include this chart in your notes. It's in section 1. But what is happening here? The liquid water is heated up. It gets vaporized as it's boiling. The liquid is converting into a gas. And the liquid water is converted into the gaseous water, which we call steam or water vapor. Again, you can reference this particular chart in section 1 where we discussed it initially. Now, one more thing I want to make before we go on to the next page of notes is that this change of state for water is a physical change. And it's a physical change here because both ice, the solid form, and water have different appearances, but their composition is the same. And we could clump that ice, water, and water vapor into this same category here. Again, this says ice, liquid water, and water vapor have different appearances, but their composition is the same. Now, before we go here, I want to add this to the top of these notes. That phase change is a physical change. So I'm going to put is a physical change. Okay? That is really important. Any one of these phase changes. So any conversion here on our chart we saw in section 1, these are all physical changes. Again, it changes the appearance of that substance, but it does not change that composition. And that is a key thing to remember in phase changes. Now, there are some terms that are associated with phase change, and I do want to go over those particular terms. So, our terms that are associated with phase change include things such as boiling, freezing, melting, condensing, subliming, and deposition. Now, it's very important to note this, that boiling and melting points are intensive physical properties that may be used to identify an unknown substance. Okay, so now we've talked in depth and in detail about our physical change and phase change, which is a form of physical change. And so now we can shift gears here to chemical change. So remember here that chemical change is defined as a process that involves one or more substances turning into new substances or converting to new substances. Now, this chemical change is referred to as a chemical reaction. Now, a key point here in a chemical change, or something that we need to identify, is this. New substances formed in a chemical reaction have different compositions and different properties from the substances before the reaction occurred. Now, just like we did with physical change, we can also associate terms with chemical change. One term is explode. A second term is rust. A third term is oxidize. Another term is corrode. An additional term is tarnish. A sixth term is ferment. A seventh term is burn. And our last term that I'll write down here is rot. So again, there are additional terms that describe a chemical change. We just list the most common ones that you see. And the major thing here is in a chemical change, the substance at the final substance is going to be different than that initial substance. So let's see this in an overall example. And that is the rusting of iron, which we've all seen or experienced in some way, shape, or form. And it's a process where iron and oxygen react together. Now, iron and oxygen are referred to as the reactants in this process. Now, as iron and oxygen react together, rust forms in this process. Now, rust, or iron 3 oxide, is a product of oxygen and iron combining together. Now, we represent this process via a chemical reaction. Now, a chemical equation shows the relationship between the reactants and products in a chemical reaction. Now, we can show this in our rusting of iron example. So how the rusting of iron would look in a chemical equation would be this. We'd have solid iron, which we represent by Fe, reacts with oxygen, O2 gas, to produce iron 3 oxide. Okay, so we would have Fe2O3, which is also a solid. Now, over here is iron, and O2 is our oxygen. And iron and oxygen, because they're on the left-hand side of the equation, these are known as the reactants. Now, over here on the right-hand side of the equation, Fe2O3 is iron 3 oxide. Now, since iron 3 oxide or rust is on the right-hand side of the equation, we refer to any substance on the right-hand side of the equation as the products. Now, I'm not too worried about this at this moment, but this equation right here is not balanced. And we'll get to that in the upcoming chapters on our chemical reactions and chemical equations. All right, so now we have our example of the chemical change and the chemical equation, which represents the entire process. What we want to do now is we want to recognize, hey, how do we know that a chemical change has occurred? And so what we do is we look at evidence of chemical reactions. Now, a chemical reaction always produces a change in chemical properties. Now, we can have some examples or signs that a chemical reaction occurred, which include the following. 1, energy changes. 2, changes in smell. Now, let's turn to a specific example that we have just gotten we just went over in depth and in detail, and that is rust, or iron 3 oxide, which is a product, has different properties than the iron and oxygen that were initially those reactants. So let's break this down by each of the 3 substances involved in the rusting of iron. Let's start out here with iron. 1, iron has a silvery gray color and is attracted to a magnet. 2, we can talk about oxygen. It is a gas and is clear and colorless. And then we can finally talk about rust, or iron 3 oxide. It has a brownish orange color. It has a powdery substance or feel to it, and is not attracted to a magnet. Okay, so we can see here, we can identify that our chemical change, or rusting of iron, the products are distinguishably different from our reactants, and they have those different properties that we've listed out here. Now, our final thing that we need to talk about, our final topic here of this section, is known as the conservation of mass. And I want to start out here talking about the conservation of mass, and specifically talking about the law of conservation of mass. And this law states that mass is neither created nor destroyed in a chemical reaction. Now, this law was found when the mass was carefully measured before and after many chemical reactions. Now, with this point here, the total mass involved in the reaction remained constant before and after the reactions took place. Now, this discovery of this law made it possible to measure by the scientific advancement of the analytical balance. So they needed that tool or that technology to be able to accurately measure chemical reactions, or the mass of chemical reactions, before and after the reaction. Now, the law of conservation of mass does have an equation. And that equation is that the mass of the reactants needs to equal the mass, the total mass of the products. Okay? Now, we have some steps to use the law of conservation of mass formula. So step number 1 is to write an equation showing that the total mass of the reactants is equal to the total mass of the products. Step number 2 is determine what you know and don't know. And step number 3 is solve mathematically for the unknown. Okay, so let's try these steps here in a few example problems. Okay, so example number 1, it says in an experiment, 10 grams of red mercury 2 oxide powder is placed in an open flask and heated until it is converted to liquid mercury and oxygen gas. The liquid mercury has a mass of 9.26 grams. What is the mass of oxygen formed in the reaction? So we need to take and we need to break down a lot of what this particular problem is saying. So what we do first is we just write out an equation using words. So it said we started out with mercury 2 oxide, and that's the only thing that we started out with. So what I'm going to put here is mercury 2 oxide. And I'm just going to write it down exactly as we see it in our particular problem. Okay, so that's what we started out with. It says it reacts. So I'm going to draw an arrow to show that it shows or it has that reaction. And it says it's converted to liquid mercury, which I'll just write down as mercury, and oxygen gas. Now, this term "and" means a plus sign. So I'm just going to put "and" or plus oxygen. Now, all I'm going to do here is I am going to add mass and an equal sign to what we have here. So I'm going to emphasize here the mass, the total mass of mercury 2 oxide needs to be equal to the mass of mercury plus the mass of oxygen. Okay, so now I'm going to list out each of these things, and we're going to figure out what do we have and what do we not have. So I'm going to start out here with the mass of mercury 2 oxide. And in my problem, it says, hey, we have 10 grams of red mercury 2 oxide. So that's what I'm going to put here, 10.00 grams, because that's what we have. And now the mass of mercury, I'm going to list it out here, mass of just mercury, is equal, it says here, liquid mercury has a mass of 9.26 grams. 9.26 grams. And in the problem, it says, what is the mass of oxygen? So the mass of oxygen is a big question mark. We don't know this. But we have 2 of the 3 variables we need. So what I'm going to do is I'm going to substitute the mass of known mercury 2 oxide into that position. So I'm going to have 10.00 grams equal the mass of mercury, which we just listed out as 9.26 grams. So 9.26 grams plus the mass of oxygen, which we put a big question mark because we do not know. Now, this is an addition equation, so that means to get rid of 9.26, we need to subtract 9.26 grams from each side. Okay? Now, you can probably do that in your head. but just to double check here, we're going to put 10.00 minus 9.26, and we get a value of 0.74. Now, this is a couple of things. Remember, significant digit rule. We lined up the decimal. They both have 2 decimals, so that means our answer needs to have 2 decimal points or 2 digits after the decimal. And then we have to have a unit, so it's 0.74 grams, and that is equal to the mass of oxygen. All right, so let's try another example with a different equation. All right, so in this problem here, it says, from a laboratory process designed to separate, keyword, separate water into hydrogen and oxygen gas, a student collected 10 grams of hydrogen and 79.4 grams of oxygen. We want to know how much water was originally involved in this process here. Now, a couple of key things that we need to take away here. Number 1, it says, hey, we are separating our water. And number 2, it says water is the original or the initial starting substance. And so what we need to do here is we need to set up our equation where water, if it's listed as the initial substance, is broken down, which we represent by a arrow there, into hydrogen and oxygen. And so, again, we see the word and. That means that we need a plus sign, so and oxygen. Now, just like we did in the last problem here, we can say that the mass of water is equal to the mass of hydrogen plus the mass of oxygen. And now all we need to do is plug in what we know and don't know and solve this equation that we've just produced. Okay, so the mass of water. If you read the problem, it says, hey, how much water was originally involved? So we don't know, and this is going to become our question mark. Now, our hydrogen, the mass of hydrogen, is listed. And if you look here, the mass of hydrogen is exactly 10.0 grams. So we have 10.0 grams of hydrogen, and the mass of oxygen is also listed. So the mass of oxygen is listed at 79.4 grams. So again, we know everything but one variable, so we can plug this into our equation and we can solve mathematically. So the mass of water is equal to the mass of hydrogen, which we can substitute in for 10.0 grams. So 10.0 grams plus the mass of oxygen, which is 79.4 grams. So all we need to do in our calculator, and again, you can probably do this in your head, but we put in 10.0 plus 79.4, and we get a value of 89.4 grams of water. So the mass of water is 89.4. And again, because we're adding, if we talk about significant digits, they both have 1 decimal. That means our answer, because we're adding, needs to have 1 decimal. All right? So I will box that in. That is our final answer here for this problem. Again, the key takeaways here is read the problem carefully, develop that, what we call word equation, and then we just substitute, hey, the mass of the stuff on the left is equal to the mass of the stuff on the right. All right, so this concludes section 3.2. Hope you have enjoyed this particular episode. And if you haven't done so already, make sure you subscribe.